Okay, so today we're going to continue to do the washer method to find the volume of a solid generated by revolving a region. And I wanted you guys to see like a side-by-side picture here. So this is basically what we've been doing so far when our cross sections were washers and continue to be washers. It could also look like this. And the reason for that, it depends on how we're revolving it around a particular line. So if we're revolving it around a line like y equals 0, which is the x-axis, or y equals b, is going to look like this. However, if we start to revolve them around a line like x equals 0, the y-axis, or x equals a, it's going to look like this. So let's go over what we've been doing, and then we'll talk about what we're going to do. Okay, so first off, our washer method, when we wrote our radii in terms of the functions, we had a vertical radius. Okay, we have vertical cross sections. That means that our radius was perpendicular to the x-axis. So we're able to express our radii in terms of x. And we found these by doing top minus bottom if you're going to write anything. This is important to remember because that's going to change pretty soon. So the volume of a solid can be rotated about any line. So whether it's the x-axis, like y equals 0, or the y-axis, like x equals 0, any line. So when it is rotated about the y-axis, okay, or any x equals a vertical line, we're going to use this new method. So let me erase some things here so it's a little bit clearer for you. Okay, and perhaps you were still writing the first slide, so you should be finishing it anyhow. Here we go. So if it's rotated about the y-axis, or again, any like x equals a kind of thing. Now everything's going to be in respect to y. So these values, well, first off, I put a v sub y instead of v sub x. These values for a and b are also y values, okay? So I'm writing it. I'm going to erase it pretty soon so you can see this slide a little bit better. But keep in mind, these are in terms of y. Now, much like the other one, you can factor out the pi from both terms, so it's a much simpler and cleaner look to our formula, or I should say equation. And both big R and little r, our radii, are in terms of y. So when we integrate, again, these are all values of y, this has to be a dy. So we can integrate with respect to y. So now, when we look at our drawing and we have a region and we start reflecting it or rotating around the y-axis or some line like x equals 0 or x equals a, you're going to have a horizontal radius. It's going to be perpendicular to the y-axis. So it's just things that are reversed from what you knew before. And so, with that being said, we're going to look at what is our right curve and our left curve to determine our radii. So instead of doing top minus bottom, like we did before, we're going to do right minus left to determine these radii. So I'm just using R minus L right now. We're going to do an example problem, okay? So just keep in mind, it's just the reverse of what we were doing before. Few things will stay the same, such as sketching and integrating. But other than that, reversed. Okay? Okay, so our example says find the volume of the solid generated when the region, and and it's bounded by our functions, y equals x squared, x equals 1, and the x-axis. And it's rotated about the y-axis, so it's rotated about x equals 0. So I'm writing it instead as x equals 0 in case you have a practice problem where it's like x equals 4. Okay? I'm going to be doing the same thing I'm going to do. I'm going to first start off with your drawing of our function. So we have our axes, and we have 1, 1. You could have -1 if you'd like. Let's draw in our first function, y equals x squared. I'm going to try to connect these the best I can. We're going to also have x equals 1. And I'm going to label this, hold on. The x-axis as a boundary. And the reason we have that is because, and the x-axis is y equals 0. It should have been a different color. I thought I picked the green. I'll just redo that. Right on top. Is so we can establish where our region is. And that would just be here. It's not going to be over there. Or here, wherever you see dots just appearing. Okay. Now we're going to revolve it around x equals 0. So find your vertical line and reflect all your points or your region over that line. Okay? Okay, so I had some technical problems, I should say very severe technical problems for this video. This is about the third time I have been doing this. So just bear with me as I will try to explain everything as brief and short as I possibly can. Hopefully still clear. Alright, so with the technical issues I have to redo my drawing. And here we go. If this is not the best drawing in the world, please bear with me. Like I said, I actually drew this numerous times, and every time I drew this out and finished this problem, it never saved, and I'm doing it again. So these are all the things that are being described in the problem, and this is the region where all three are boundaries. So this is the region we're going to revolve around the y-axis. And we usually don't have this symbol. You don't need it, but it is helpful when you have to try to imagine what your region is. And it's important to know where you're revolving it around. So your region ends up kind of reflecting over here. And you can see now that if you have to do a cross section, it's going to end up being a washer. So washers are now looking in this way, as I was indicating in our previous lesson. It would look like this. And in our last few slides, it was also indicating, hey, our radius is going to be functions of y. So your radius is going to be going this way. And for this radius, if we had to measure it out, it's going to be measured by doing right minus left. So it's going to be touching the line y equals 1 on the right side and the line that we're rotating it around, which is x equals 0. Okay, these are functions of y because they're x equals equations. They're not functions of x. So now, keep that in mind. Always one of these should be the line that you're revolving it around, just like in the other problems. So whether it's 0 or 4, whatever value x equals, it should be one of these. Now right minus left again for the smaller radius. And we're starting to use this function, okay, and x equals 0. But this is a function of x right now. So we have a little bit of an issue. This is not, because it's x equals 0. It's not a function of y if we write x squared here. So we're going to instead solve for x, so it's a function in terms of y. Now, when you put in the square root, you have to put in the plus minus. But because our region is only here, we reject that negative. And we're only using that positive square root of y. So you can see now it is indeed a function of y, and we can proceed to use our formula. And we want to say v sub y, and we want to write y equals in the upper and lower limits of integration. Now we're integrating with respect to y. So keep in mind we also not only have to look out for this little issue here, but where our region starts to be shaded in to where it ends in terms of its y values. So starting down here on the x-axis, it ended up here where our curve met our line x equals 1. And that's where y is equal to 1. So remember, they're not the x values. Big R squared minus little r squared. And this actually becomes a little bit easier to solve than you probably thought before, because it's going to simplify very nicely. This is just 1 minus y, and so we can easily integrate that and plug in 1 and 0. I lost my equal sign. This is just going to be 0. So 1 minus a half is 1/2. And so our volume is half of pi, or pi over 2. And that's it. Okay. So little things to kind of give you a heads up. Let me know if you have any questions. And if you are revolving it around a line like x equals 0, or x equals 4, or x equals whatever a value, just remember that's got to be in here in this section somehow, okay, like the 0 was. So, and remember right minus left. Good luck.